The last major component is to determine the stress and strain and deformation when you have a statically indeterminate axially loaded member. This means that you have a member that has supports on both sides, so that when it creates a deformation, it can't really actually move, but that deformation is going to cause additional stress on the member. So this means that there's fixed supports at both ends. So therefore, we're going to have equations of equilibrium that are insufficient to solve the system. So this is because our number of unknown forces is greater than our equations. So what are we going to use then to come up with an additional equation to be able to solve these problems? Deformation equations, because we know here that the deformation, total deformation, is going to have to equal 0. So let's look at an example. We have a rigid plate at C, a rigid plate at C that's being used to transfer a 20 kip weight, or a 20 kip load, to a steel rod. So this rod down here. So the E of this rod is 30,000 KSI. Oh, that's A. Sorry, this rod. And an aluminum alloy pipe B. So EA is equal to 10,000 KSI. The support at the top and the bottom are rigid, and no stress, there's no stress in it before loading. We're given that the cross-sectional area here is equal to 0.8 inches squared, and the cross-sectional area here is 3 inches squared. We need to find the stress in A, the stress in B, and the delta C, or how far this plate is going to move down. So even though the overall deformation here has to be 0 because these are fixed, this plate can move up and down based on this load. So what we need to do here now is draw both a free body diagram, like you do for all your other problems. So our free body diagram is of the plate, and so you cut off, this is the only time you get to cut off twice. So we're looking at the plate, we cut it here, and we have the internal load created going up from the pipe A, and then we have the internal load coming up from the pipe B, and we have the two halves of our 20 kip load pushing down on that rigid plate. But then we also need to do a deformation diagram. So the deformation diagram looks like this, where we're showing here that we're pushing down, so our deformation is going to be downward for A, but then deformation of B also has to be downward. So this rod is essentially going to go down, and then so is this part B. So the deformation of this pipe A going down is equal to the deformation of B going down. They have to equal because nothing's actually going to move. So, looking at this free body diagram, let's do our equations of equilibrium. If we sum the forces we have PA plus PB minus 10 is equal to 0. So from this we have PA plus PB is equal to 20. We don't have enough equations to solve this problem just by looking at the free body diagram. So now if we write our equations for the deformation, we can end up solving for this. So if we have that the deformation of A is equal to the deformation of B, we can use this equation, PL over AE, and solve for those. So we have the deformation of A, which would be the force at A, times the length of A, we have 10 inches, over the area at A, which would be 0.8 inches squared, and the E for A is 30 times 10 to the third KSI, or 10 to the 6th PSI. And that is going to equal my deformation of B. PB, and then the length is 20 inches, over the area, which was given as 3 inches squared, and the E for part B is 10,000 KSI, or 10 times 10 to the 6th PSI. So now we have two unknowns in this equation and two unknowns in this equation. So if I solve one of them for one of the unknowns, so I solve this one, PA is equal to 1.6 PB. Now I can put that back into here, PA into here, and solve for PA. So doing my algebra, I will then end up with PA is equal to 7.7 kilonewtons, and PB is equal to 12.3 kilonewtons. Then using that stress is equal to force over area, I get that the stress in A is 15.38 KSI, and the stress in B is equal to 2.56 KSI. So now what I want to know is that's one part of it, or two parts of it. The last component, they want to know what the deformation is of the plate at C. So that is going to be the same as we get for A or B, either one. So we have 12.3 times 10 to the third which is my load at A, times 10 inches, which is my length of A, and then my area, 0.8 inches squared, and my E, 30 times 10 to the 6th PSI. So I can solve for that total deformation, which is 0.005 inches. So when you have statically indeterminate, which means there's supports at either end, and you can't solve for all of the forces from your free body diagram because you have too many unknowns, you can also use your deformation diagram because the overall deformation has to be 0. So that means that these two deformations have to equal each other, and that is how you do statically indeterminate.